V equals IR. V equals IR. V equals IR. If you remember nothing else from this video, remember that. Welcome to Introductory Electromancy. Why learn electronics? Well, there are three main reasons: phenomenal cosmic powers, stable knowledge, and immediate application of concepts learned. Let me break those down. As far as the phenomenal cosmic powers go, you can give inanimate objects the ability to perceive and interact with reality. Given advancements in neuromorphic architecture, particularly analog neural processing units which store synaptic weights in memristors or floating gate MOSFETs, you may be able to graft external neural processing capacity to yourself through invasive implants or bidirectional electrocorticography. This clears the way for enhancing your mental abilities by adding pieces to yourself, creating a hybrid cybernetic organism by connecting multiple brains, or gradually transferring your consciousness to a synthetic substrate, allowing you to become both autotrophic and functionally immortal. As far as stable knowledge goes, well, Ohm's law has remained valid since it was first published in 1827 by Georg Ohm. Unlike many other scientific fields, the fundamentals of electronics will probably not need to be relearned, so time spent learning the basics should remain valid and useful to you for your entire life. As far as immediate application of concepts learned goes, in most fields of study you have to wait months or years to apply the concepts that you've learned to real life. Nuclear engineers and astrophysicists have years-long wait times before they can put their knowledge to work in a practical setting. In electronics, with a solderless breadboard and appropriate stock of parts, you can go from seeing a schematic in a textbook or on the internet to watching it operate in front of you in real life within about half an hour. I worked as a math and engineering tutor for several years. I've also been building and studying electronics for about 20 years. My prototypes, schematics, and code have been included in the Arctic Code Vault, featured on Hackaday twice, and cited in the Croatian Medical Journal. Admittedly, that citation is because they thought what I was doing was dangerous and unethical, but it still counts. You can refer to my instructables and GitHub pages to see what I've made, documented, and publicly released so far. They're linked in the description. The intention of this video series is to bring you, dear viewer, to the same level of skill and understanding so that you can then surpass it and build a better world. Our world is something of a giant collaborative project. Almost nothing around me is natural in origin. It's all been made by humans or machines. I think the only natural thing I have in arm's reach is this piece of birch bark. So, as a species, we've now built this huge artificial environment that we occupy, and we all take turns working on it. It's a team. We're all supposed to be on the same team. With this information, please do not build anything you wouldn't want used on yourself personally or on your loved ones. There are a lot of things that engineers have built that I am not particularly proud of. Landmine anti-tamper mechanisms are the first thing that comes to mind. That said, to the extent that we will be following a textbook for this, it is this one, the Tab Electronics Guide to Understanding Electricity and Electronics, 2nd edition, by Mr. G. Randy Sloan. Don't get the 1st edition. This is like the one textbook where the 2nd edition is actually significantly better. As far as I know, it only has errors on 2 pages. Well, 4 pages. It has 2 errors. They are split between 4 pages. On pages 207 and 208, Mr. Sloan mixes up silicon-controlled rectifiers and Schottky diodes. And on pages 363 to 364, he mixes up bytes and words. A byte is always 8 bits. The word length varies depending on the processor architecture. Beyond that, as far as I know, everything in the book is accurate and correct to the best of my knowledge. So this book will be the majority of what these instructions are based on. As we get further, I will start bringing in things from digital logic and state machine design by David J. Kummer. Looks like this is the 3rd edition. Additionally, depending on where you are in math, you might find use in the Cartoon Guide to Algebra. I will also be pulling from the Cartoon Guide to Physics and the Cartoon Guide to Chemistry. If you want to get very fancy with it, you could get the Feynman lectures on physics. The math involved is pretty involved. There is a Cartoon Guide to Calculus, but it doesn't cover the del operator, which Feynman uses because he believes in being very fancy. Look at him. His bongos, all fancy. Anyway, this is optional. Also, note that this is the Indian subcontinent edition of the book, which is a lot cheaper than the edition circulated in the US and has the same information. But yeah. So, where to begin? Very complicated. There are a few more materials that I will be linking in the description, which I have accumulated over the course of a long time. There are online math resources which you might find useful. Purplemath, Khan Academy, Mathisfun, Wolframalpha, which was fancier before they started charging people a subscription fee for step-by-step solutions. For online electronics resources, you can look at Adafruit Industries, SparkFun, SparkBang Buzz, Evil Mad Scientist Labs, Big Clive, Hackaday, or Instructables. Now, I'm going to start from the very beginning to the extent that I can. I'm sure that I will forget things or leave them out. Let me know. If I do so, I will try to correct any errors or oversights. Let us begin with this, our pale blue dot that we inhabit, and also a 9-volt PP3 battery. It has a little symbol for it. But what is the little symbol? I am just now working on getting this setup optimized, so please bear with me. Schematic symbol for battery is this. That right there is the symbol for a battery. It is similar to the symbol for a single electrochemical cell, which is just a stubbier version of it with only one of those things. The symbol for the battery has 2 in series. In reality, it can represent more than 2. This 9-volt, for example, has 6 cells in series. Now, in electrical schematics, the lines mean wires. So if we wanted to design a circuit with this, we would use lines to represent our wires. Say we wanted to add a switch. This is the symbol for a switch, specifically the symbol for a single pole, single throw switch. Here are some switch types that you might see in the wild. Single pole, single throw, single pole, double throw, which has a single contact that can be switched between 2 different outputs. Boy, my handwriting this is all going to take some practice. And then you might also see a double pole single throw switch, or a double pole double throw switch. So now we have a battery and we have a switch. The physical switch that I'll be using is this Nintendo Switch that I gave to my kid a few years ago for Christmas. He was not thrilled with it. But this is a single pole, single throw switch right here. In order to connect to our battery, we'll be using this nifty 9-volt clip connector. Note that it has 2 colors of wire coming out of it, red and black. Generally, red is positive, black is negative. Generally. In most applications, it is recommended to test this with a multimeter yourself before you start relying on it, because manufacturers just want to produce a working product, and they often use whatever wire is on hand, so the colors can be random, since the electrons themselves do not care about the wire color. So there will be a battery, a connector, and a switch. So far, this is all we have for our schematic. For this first project, I'm going to have us build a simple continuity tester. It checks if something is electrically conductive. Because this circuit will be based on a 9-volt battery, it's not actually safe to use it on lower voltage electronics because it'll try to run 9 volts through them. Later on, we can make a fancier version that has a lower test voltage output. But as this is an introduction, I'm going to use the simplest version available. Now, in order to make this work, we need to complete this circuit, and we need some sort of indicator. I'm going to use an LED, light emitting diode. Later on, when we talk about semiconductor diodes, I'll explain how they can emit light. In fact, all diodes emit light. It's just that regular silicon diodes emit infrared light, and they're usually packaged in opaque packages. But this is the symbol for an LED. It's got the two little arrows to indicate that it's emitting light. And it's this arrow-looking thing with a line at the end. Now, the device under test is going to go here in the circuit. This is not a standard symbol. It's just what I'm using to indicate. So your thingy that you want to test the continuity of goes there. See, I need to refill my pen. However, if you simply wired this up as it is, the LED would be destroyed. A regular LED can handle about 20 milliamps. To be safe, 30 if you're pushing it. Beyond that, you begin to severely decrease the life of the little semiconductor chip in it. So we need a current limiting resistor. In series. That's the symbol for the resistor. A squiggly line. Now note that that's the US symbol for a resistor, but in Europe and elsewhere, it'll just be a long rectangle. I usually use the squiggly line symbol because it is faster to draw. Now, this resistor value, I'm just going to make it around 1 kilo ohm, which is 1,000 ohms. The LED color doesn't really matter. Red is a common and standard color. Shows what I get for not refilling my pen before this. Anyway, so now we have a schematic. We need to find parts for it. It's easiest to organize your parts in boxes intended for organizing beads, at least in my experience, because they have handy sub boxes. Get red LED. LEDs only work one way around. They have a positive and a negative terminal. Usually, the negative terminal is attached to the bigger metal piece inside. The other way to identify it is that there will be a flat on the case of the LED next to the negative terminal. Also, when they're packaged with loose leads, the longer terminal is positive. The shorter one is negative. If you look at it from the top, you can see that it is flat on one side. Maybe. Perhaps, yeah. See the little flat on the left as opposed to the plastic making a round shape? That flat is what indicates the position of the negative terminal. Alright, so one red LED. We will also be needing a 1 kilo ohm resistor. There is a whole resistor color code to learn. It's black, brown, red, orange, yellow, green, blue, violet, gray, white. But for this, The 1 kilo ohm LED is not focused, because why would it be? Brown, black, red, gold means 1,000 ohms plus or minus 5%. The physical sizes of the resistor are connected to how much power it can dissipate. The quote-unquote standard, the smaller ones in my box are 1/4 watt, bigger ones are 1/2 watt. In actual application, these things get pretty hot if you make them dissipate 1/2 watt of power. So it's not really recommended to do that. Okay, so now we have our parts. Get some nice output leads. And we wire it up. If this were a more complicated circuit, the way that it would work is you would design it on paper or on a computer. That is your thing. I have better luck drawing schematics on paper because it makes me think about them in a way that arranging them on a screen doesn't, so I often catch errors that way. Start on paper, then you would move to the solderless breadboard, which I will be covering in more detail later. Suffice it to say, these little rows of 5 holes are all connected, and then the longer rows that have blue and red lines next to them are also all connected. So you connect your power and ground there, then plug individual components into here to connect them to each other. Like this Arduino Nano, for example. Then, after building something on the breadboard and verifying that it works, you can move it to perfboard. This is a pre-built circuit board, but it has no connecting traces, so you can stick components through the top, then solder them on the bottom, and then bend the leads themselves to form the circuit that you want to build. It's a good way to rapidly prototype your designs without having to wait several weeks for Seed Studio or another offshore board manufacturing company to build your design and ship you the circuit boards. So now we have our components and our schematic, and we are ready to start soldering. Someday I will have a proper phone holding rig instead of just leaning it against my solder, but today is not that day. So let's see if I can do this without it going horribly wrong. Fun times for all. Okay, so far so good. Now, I am using TS100 soldering iron by Min and a TS-I tip. It's the finest one they make. I prefer finer soldering iron tips. It becomes a matter of personal preference. As far as the solder itself, the alloy is called SN100C. It's a lead-free solder alloy. Now that we are in the future, leaded solder is no longer necessary. 0.032 inches is a good common diameter. And then as for the flux, it is NC601 flux, which means no clean. So you can leave it on the board after using it without causing problems. There is a lot that goes into solder and how it works. You have the wire itself. This is, I believe, tin, copper, nickel, and germanium. And then the flux in the middle, when it gets heated and flows over the metal, it cleans away the oxide so the solder can bond to it properly. You can get acid core solder. Don't use it for electronics. It will, the acid dissolves metal. So even if it's fine initially, residual acid from the solder will eat away all of your wires and connections. It'll be a whole thing. So don't do that. That'd be bad. Now this soldering iron can be powered from a wall transformer, or in my case, this very, very safe, totally not bulging lithium polymer battery pack. Safety. That's what we've got here. And then you'll also want some of this stuff. It's for cleaning the tip of the soldering iron. Works better when it's hot, naturally. But you just poke it in there and it scrapes away any dross or buildup of oxidation. And you'll want some sort of container to tap your liquid solder into, which will become clearer shortly. So, for this alloy SN100C, I use a 350 Celsius iron tip, so we have to wait for that to heat up. Let's see if I can show this to you and keep it in focus. Not very well. I need some sort of backplane. Alright, so once your iron has heated up, begin by melting some solder onto it. And then it should stick to the iron tip like so. Knock off excess. Clean the iron tip. Apply a little more solder to it. The process of having a little bit of solder on your iron tip to begin with, called tinning. It flows a lot better if you do that.